Okay, we're ready for part 2 of section 4. I just want to review some of our basic rules for testing for symmetry. How do we know if a graph is symmetric in a particular way, be it over the y-axis or over the x-axis or whatever? If it's symmetric in the x-axis, then you should plug in negative y for y. Switch your y values. If it's symmetric in the y-axis, you should substitute negative x for x. Switch your x values. If it's symmetric in the line y equals x, then you switch x and not h. Just realize that. You switch x and y, not h. My bad. Alright, and if it's symmetric about the origin, you substitute negative x for x and negative y for y. Negative x for x and negative y for y. Alright, so I've given you an interesting graph here. I've given you the graph of x squared plus xy equals 4. And I want you to test it for symmetry in the 4 options. Test it for symmetry. See if it's symmetric. So here's what we do. To test it in the x-axis, you switch negative y for y. So leave x squared alone plus x times, instead of y, put negative y. And then simplify. You get x squared minus xy equals 4. And what you do is you look to see if that is the same as your original graph, your original equation, yes or no. And if it is, then you know the graph has symmetry in the x-axis. Well, x squared plus xy equals 4 is not the same as x squared minus xy equals 4. So we would say no, the graph does not have symmetry in the x-axis. And then you just kind of repeat this process. Test it for symmetry in the y-axis. So now you're going to switch negative x for x. So instead of x squared, you're going to put negative x squared plus negative x times positive y equals 4. And clean that up a bit. Well, negative x squared is just x squared, but negative x times y is negative xy. Is that the same as your original graph? He's got a minus. The original guy had a plus. So again, we would say no. This graph is not symmetric in the y-axis. How about the line y equals x? Well, here you switch x and y. So instead of x squared, we're going to put y squared plus y times x equals 4. So now I have y squared plus xy equals 4. Well, that's certainly not the same as what we started with, because we started with something that had x squared, not y squared. That's just silly. So we're going to say no. He does not have symmetry either. Man, we can't find any symmetry for this graph. Well, let's try the origin. In the origin, you substitute negative x for x and negative y for y. So instead of x squared, I'm going to put negative x squared. And instead of x, I'm going to put negative x. And instead of y, I'm going to put negative y. Well, negative x squared is just x squared. And negative x times negative y is really plus xy. Uh-oh. By the way, that should equal 4, not 0. Is this the same as my original equation? It is. So this does have symmetry in the origin. It does have symmetry in the origin. The graph does. Well, let's sketch the graph and just get a picture of what it looks like to have symmetry in the origin. Here we go. Alright, what I would do is solve the original equation for y. Alright, so what I would actually recommend here doing, how would you solve this for y? I would factor out an x. That leaves you with x plus y. Now you can divide both sides by x, so you get 4 over x. And then you can get y by itself. So it really says y equals 4 over x minus x. And the reason I did that is because now I can make a table and just plug in some x values and get some y values. So let's leave all our original ordered pairs alone. Plug in 1. If you plug in 1 for x, you get 4 over 1 minus 1. That's 4 minus 1, which is 3. Plug in 2. You get 0. Plug in 3, you get negative 5 thirds. Plug in 4, and you get negative 3. Now, I did that rather quickly. It's because I already had it done. But I assume you guys can plug in values for x. But now, remember, it had symmetry in the origin. it had symmetry in the origin. That means all your ordered pairs go from xy to negative x, negative y. Negative x, negative y. So what will those ordered pairs look like? Because they're also a part of the graph. Instead of 1, 3, it's negative 1, negative 3. Instead of 2, 0, it's negative 2, 0. Instead of 3, it's negative 3, positive 5/3. Instead of 4, 3, negative 3, it's negative 4, positive 3. All of these ordered pairs are on the graph. So now let's sketch a graph with all those ordered pairs. So I'll do the original ordered pairs first. 1, 3, 2, 0, 3, negative 1 and 2/3, right about there, and 4, negative 3, right about there. So it's kind of a funky curve looking thing, but that's only the first half. Remember, this was symmetric in the origin. You got to graph the other half too. Negative 1, negative 3, negative 2, 0, negative 3, 1 and 2/3, right about there, and finally negative 4, positive 3. And whoop, kind of missed the dot there. Let's just make the dot bigger. And there you go. That graph is symmetric in the origin. Symmetric in the origin. Kind of funky, huh? That'd be difficult to do on your graphing calculator. I'd have to teach you some pretty nifty tricks. Okay, this is the last example I want you to do. I want you to test this equation. It's a crazy equation for symmetry in all four places. Okay? So the original equation is absolute value x plus absolute value y equals 3. So for the x-axis, I'll leave x alone, but replace y with negative y. Well, what's the absolute value of negative y? Well, that's just the absolute value of positive y. So we would say, yes, it's got symmetry in the x-axis. Try the x-axis. So now switch your x values. Does that become absolute value of x plus absolute value of y? It sure does. So we would say, yes, it's got symmetry in the y-axis. Well, that's interesting. Now, the line y equals x. Switch. So now it becomes absolute value of x plus the absolute value of y. Well, is that the same thing as absolute value of x plus the absolute value of y? Sure is. Cool. And then finally, what about the origin? So now I have the absolute value of negative x plus the absolute value of negative y. Remember, that's the change you make for the origin. Well, that's just the absolute value of x plus the absolute value of y again. So it has symmetry in all four possible ways. Well, what I would recommend doing is placing a few values. If x is 3, what's y? Think about that. If x is 3 up here, y must be 0. If x is 2, y has to be 1. If x is 1, then y has to be 2. And if x is 0, then y has to be 3. Let's sketch that. Dun, dun. So, 3, 0, 1, 2, 3. 1, 2, 3. 1, 2. 2, 1. Boom. It's a piece of a line that has a slope of negative 1. Alright, but remember, it has symmetry in all four places. So, we need to switch the y values. So, instead of 0, 3, we get 0, negative 3. Instead of 1, 2, I got 1, negative 2. Instead of 2, 1, I got 2, negative 1. Boom. It kind of looks like an arrow tip now. Oh, wait a minute. I can also switch the x values. So instead of 0, 3, I still have 0, 3. Instead of 2, 1, instead of 1, 2, I have negative 1, 2. Instead of 2, 1, I have negative 2, 1. And instead of 3, 0, I have negative 3, 0. That's me switching the x values. But wait a minute. It's also symmetric in the origin, which means I can make the x's and the y's negative. So instead of 1, 2, I have negative 1, negative 2. And instead of 2, 1, I have negative 2, negative 1. So that graph actually ends up looking kind of like a diamond. It's actually a square turned on its side, or turned on one of its corners. Pretty cool. It's the power of symmetry. Symmetry is a very, very powerful tool that will help you not just this year in pre-calculus, but next year in calculus. Hope you all are doing fantastic. That's all I got for part 2. Have a great night. I'll catch you later. I'm out.